In this discussion video, we're going to do some solving equations examples. So I want to look at problem number 8, parts A, B, and C from worksheet 1. So let me zoom that out a little bit so we can see all three of these. And first, I want to give you an opportunity to try each of these three questions. So overall, pause that video for about 4 minutes to try these three. 4, 3, 2, 1. Pause the video for 4 minutes and give yourself a little bit of time to try each of these parts. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 4 minutes. Let's talk about these together now. Alrighty, so for part A, we have 4 to the 2x plus 1 equals 16, and 16 is 4 squared. And when I have the same base and being raised to a power on both sides, I can at this point say that these powers must be the same. So 2x plus 1 will be equal to 2. And if I isolate the x, we'll first get 2x equals 1 and divide by 2 to get x equals 1/2. And that's our answer. Alrighty, so that is part A. Let's move on to part B. So a little bit more complicated this time. We have 16 to the 2x plus 1 equals root 8. So this time those bases aren't the same. So we could try to maybe get a common base. If I have an exponential equation and the bases aren't the same, we can try to get a common base. And if I look at the 16 and the 8, there is a common base, and that's 2. 16 is 2 to the 4. So that whole thing is going to be raised to the 2x plus 1. And then 8 is 2 cubed, and that's inside of a square root. But a square root is a 1/2 power. And from here we have the setup, and now we can use some exponent properties. So I'm just going to write a dot, dot, dot. So from here, it's not too bad. And I'm going to leave this for you to try. So I mostly wanted to remind us what the key idea was. The bases aren't the same. We could try to get a common base. And here we were able to. All right, so now let's move on to part C. This time we have 5 to the 2x plus 1 equals 16. So with 5 and 16, there isn't a nice common base like there was in the previous question. No common base. There is no common base here, so I'm going to put a sad face. When I have an exponential equation with no common base, that is precisely where we need to use logs. Okay, so I'm going to solve this actually in two ways using logs. So the first way, I'll call this solution 1. Solution 1 is I have something in exponential form. I can transform it into log form. So the base of the power, the 5, becomes the base of the log. And then the roles of the input and the output get changed. So the 2x plus 1 is what's being plugged into this exponential. So that becomes the output of the log. The 16 used to be the output of the exponential, and now it's going to be the input of the log function. All right, and now I'm going to isolate x. So I subtract 1. Log base 5 of 16 minus 1 equals 2x. And then I divide by 2 to get log base 5 of 16 minus 1 over 2 equals x. And that is how I would leave my answer. Okay, if we needed to, we could use a calculator to help us evaluate what log base 5 of 16 is. Often calculators can't do stuff like log base 5. They can usually do log base 10 or log base e, which is ln. So we may need to use change of base if we needed to evaluate this with a calculator. But for our purposes, it's fine if we leave it like this. Okay, so now I want to talk about a second solution. And in the second solution, we are going to take the log of both sides. So before I do that, I want to do a brief review. So when I take the log of both sides, I get to choose what base to take the log, to let the log have. And the most common ones are, remember that if I write log of x, that means log base 10. Log base 10 of x. And then remember that ln of x is a special log. That means log base e of x. And e is this special irrational number. It is approximately 2.718. Okay, I'm going to put this in a little bubble. And there's something about e that makes it special in calculus, and we'll see that later in our course. Okay, so I'm going to take ln of both sides. So ln of 5 to the 2x plus 1, and that's going to be equal to ln of 16. So on the left-hand side, I have this power inside of the ln. I can move that to the front. So get 2x plus 1 in front of ln of 5. This equals ln of 16. And now let's divide by ln of 5. So 2x plus, let's not put the parentheses once I divide it, equals ln of 16 over ln of 5. And now I'm going to do two things. I'm going to subtract 1 and divide the 2. That'll give me x equals ln of 16 over ln of 5. Subtract the 1 and divide by 2. And that is our answer. These two answers that we got are actually the same. They look a little different, but they're in fact the same. And maybe you might recognize, well, why are they the same? I want to make a note of that. So with log base 5 of 16, if I did change of base, so using change of base, we would get a fraction. We'd get a log on the top and a log on the bottom. And if I made that log base e, it would be an ln. And the 16 is what goes on the inside of the log on the top. The 5 is what goes on the inside of the log on the bottom. And now I can see that, wait, these are actually exactly the same. All right, so let's end with one last example that's different flavor from the previous ones. This is question 9c from the worksheet. Solve x to the 4th minus x squared minus 20. I want to have you first try the problem. So I'm going to give you 3 minutes for this. 4, 3, 2, 1. Pause it and try this one for about 3 minutes. Alrighty, so hopefully you tried this one. This one's a really good practice question. So the one thing I want to notice about this is this is not as simple as being like a quadratic or something like that. But I noticed that x to the 4th is x squared squared. And then I have minus x squared minus 20 equals 0. So this is actually a hidden quadratic. So with a hidden quadratic, I noticed that this x squared is showing up now in more than one spot. I'm going to substitute for that. So let's pick a new variable for that. Maybe I'll pick t, and I'll let t be x squared. And if I substitute that in, we'll get t squared minus t minus 20 equals 0. And this factors nicely. This becomes t minus 5 times t plus 4 equals 0. And from here, I get t is equal to 5, or it equals negative 4. I'm not done yet because this is what t equals, and I introduced the variable t. The original variable was x, so I need to plug back in to know what x is. So I'm going to plug back into my substitution. So thus I get either that x squared equals 5, or that x squared equals negative 4. If I square root both sides of this, I get x will equal, remember, when I even root both sides of an equation, I got to put a plus or minus. So I get plus or minus root 5. And then from this other equation, x squared equals negative 4, I might recognize, wait, if I square root both sides, I'm going to get an imaginary number. And we are not allowing imaginary numbers in our class. And that would be fine. There's a quicker way, though, which is to say, oh, there's no solution, since x squared is always greater than or equal to 0. There's no way it could be equal to a negative number. And that's true because we are not using complex numbers in this class. If we were using complex numbers, we would have answers from this. They would actually be plus or minus 2i. Alrighty, so overall for this problem, the solutions are plus or minus square root of 5.